Everybody, this is Marco Reis from the University of Coimbra, a past president of Indus, wonderful chemical engineer. And again, there are wonderful statistical engineering problems within chemical engineering. So, Marco, the floor is yours.
Very good. Thank you very much. So thank you for inviting me. It's a great honor and pleasure to be in this ISEA forum. So the topic of my talk you already presented. Now I wish I was talking about process monitoring and fault detection, because I would have something to say about what just happened. But actually, this is an important topic for industry and something that we are working on. And so I will bring some case studies where we are addressing, quality prediction for different purposes. So basically, the idea of this presentation will be to introduce what are soft sensors, then to bring 3 different case studies. I mean, I try to make them relatable so that we don't have to waste too much time in the warm-up phase of this case study. So they have some similarities, but they clearly are starting from a different point to build the models. So I try to cover different perspectives of building the soft sensors. And if I have time, in the end, I will address some of the other challenges that we are also working on today. So basically, in the chemical processing industry, quality assessment is usually something that is not easy to be done. It requires complex protocols, because you have to collect the samples from the process, and then they have to undergo a lot of pre-processing and quite convolved experimental procedures in order to get in the end the measurement you want. Usually you use gas chromatography or some other type of methods to get the properties that you want, for instance. So you can imagine that they are intensive in specialized human resources, they are expensive, they are time consuming, and they are collected at quite low frequencies regarding what you would wish. And consequently, you probably don't have as much process control as you wish if you want just to use this output as a target variable, because you don't have it with the frequency that you will need and will like in order to set the inputs so that the output match your target. And therefore you also have more variability. The efficiency is also hurt because you don't have the ability to release all the products until you know what is on that stream. So you need for that the quality measurements. You have, of course, a higher risk to have off-spec products, and there is also sometimes a hidden logistic cost that is tremendous, because until you know what to do with your streams, you have to put it in very, very large vessels, and that is something that costs a lot of money. And also you have to have that vessels, and that is something that is really very costly. So there are all the motivations to make these measurements available as much as possible in real time. So what you do is to build models to predict those variables. And these models in the end are implemented in pieces of software or code, so they call it soft sensors. It's not really a physical sensor, it's a model implemented in software, and we call it soft sensors. So you can build a model like that using first principles. You can, or mechanistic models, that as we also can call it, or you can use the data that you have, and they are data driven, or today this is becoming more and more used. You can use all the things that you can bring to the model, and you have an hybrid approach, first principle and data driven all together. So in this talk, we are going to address mostly the data-driven soft sensors. But even in the data-driven soft sensors, you can have different categories. And most often, you are probably using just industrial data that you can quickly grab from your databases, like the sensors from pressure, temperature, flow rates. They are quite easy to collect. Even measurements like pH and conductivity and others that nowadays are also quite handy. You can also collect them. And so one type of sensors is to build models from these easily obtainable data in order to predict your response, your property of interest. Other types of soft sensors start not from the data that is already available, but from data that can be collected using specific technological instrumentations like the NIR, RAMA, and other types of technologies. We call it in general process analytical technologies. And to use that data, those spectra that you collect from these devices to build the sensors that you need to predict your properties. So these are like another type of sensor, but usually you need technology for that, but we also need a very good model in order to correlate the outputs from the technology with your desired output, which is your quality response. And I will also address ways of combining both types of soft sensors. So yes, so the goal is to present case studies, real case studies, where you can, put forward these 3 different ways of building soft sensors. And in the meantime, I will try to bring some relevant aspects that you have to take into account while you are addressing each type of soft sensors. And hopefully, in the end, I will also give you some feedback on things that are currently being considered as interesting topics for research. Some of them are still open, but for sure, I think they will deserve more efforts in the future in order to be, properly addressed. So the first case study regards industrial soft sensors, and by this I mean using, data that is readily available from the database. So here we want to predict RON in a reforming unit. So RON is the research of the number. I'll in a minute say what it is more specifically. But a reforming unit is basically one part of a big refinery where you convert the naphtha into something with more value. So, and basically naphtha is composed by linear paraffinic hydrocarbons, and they don't burn too well in the motor. So what you want to do is to put more branch hydrocarbons there, and also some more aromatics. And you can do that in this unit, the reforming unit. So basically, you take your stream, you preheated your stream in this heat exchanger, then you heat it up in a furnace, and then it undergoes several stages of reaction. The reaction is endothermic, so you have to provide heat to the streams, and that's how these furnaces, this H1 and H2 are doing. And in the end, after this reaction takes place, you came back again to the same heat exchanger, and you preheat the feed stream, and then you get in the end your reformate. And hopefully this reformate raises the RON number, and you can have the full with the properties that you want. So in this process, we analyze 41 variables, just process variables, over almost 2 years of production. And RON is measured, following the usual standards, the ASTM standards, using combustion research engine that is calibrated. But this is really a complex way of measuring the properties, and so this is only done a few times per week. So this is, as you can imagine, a massive facility, but the outputs are not all available with the frequency that we would like. So there is a big driver for having this property being estimated. So what we have done is we have collected data. So as you can imagine, in process data, you have to do a lot of preprocessing. You have to remove all the periods where the process was down. There is a lot of, outliers that are nonsense, and you have to filter them out. because it's just things that happens in the sensors locally, and then you have to remove that. And you also have to be careful, because you don't want to remove others that look like those and are really not outliers or faulty. So you have to tune these filtering operations very well, and you should not rely in blind ways of removing outliers, because you might be throwing away also very useful information. So we use here banks of adaptive filters, and then we always visually confirm that they were doing what they should. Another preprocessing stage that is important is where you define your granularity, because most of the times the data doesn't have the granularity that you need for your proposal. So if you use here the Ron Kennett and Shumeli approach of InfoQ, so what you want in the end is to generate as much quality of information as possible. And that means that you have to get the correct data, apply the correct algorithm, given the goal. And here our goal was, I didn't mention that before, was we want to study the catalytic activation over time. And that might take years. So for this particular goal, being able to predict RON on a daily basis is more than enough. So we set the resolution to the day. And that's always goal dependent. For other proposals, we might use another different resolution. But for our goal, the daily resolution was enough. And of course, you also still have some missing data to handle. And here, by missing data, you usually resort to methods that explore some sort of redundancy in your data sets, either in the variables or in the time. And in this case, there is a lot of autocorrelation, because these are really massive units and you are sampling them so fast. So there is a lot of autocorrelation. So we mostly do here interpolation to fill out the missing the missing data that we need to build a more stable model. And that's usually, that takes a lot of time, and that the 80% of time principle also applies here. But most of the times when you talk about soft sensors, you just focus on the modeling stage. That's what we are now being discussed. And when you get to modeling stage, quite often people apply here their favorite predictive methods, or sometimes they have a favorite set of tools that apply here. And what we have been learning is that we should be agnostic when we really don't have much information about which models to apply. So what we have done here was to develop a tool that explores different corners of the analytics domain. So we assemble a selection of different categories of methods, including variable selection methods, penalized regression methods, like lasso, elastic net, Reis regression, latent variable methods like PCR, PLS, and also tree-based ensemble methods, like random forest, boosting, bagging. And the first three categories are most for linear processes, and the fourth one addresses nonlinear processes. And this will be also our way of knowing if some nonlinearity is present, because if some nonlinearity is present, then we should bring more nonlinear methods that are not here. So we build a framework that basically compares all these methods with the data sets that we provided, and we use a double cross-validation approach that was robust enough, and then we analyze all the results and compare them. And in this case, for instance, what we got was that the three ensemble methods were clearly the best. So we were not foreseeing that they were, because we think that linear methods will perform better, because this was supposed to be under well controlled, and it is well controlled, but still there is some nonlinearity there. And so you can clearly see that. And you can fix that number that we can achieve prediction accuracies of the order of 0.4. And the kind of methods that we apply, they allow us to see which method performs better. In this case, it was random forest. And there is reasons for that, but I will not have time to cover it here. So basically, what we can do with these models is something like this. We can predict with a 0.4 accuracy, which when we compare the literature is, is well placed, is not the state of the art. There is one that could be better than ours, but that use much less data than what we did. So I don't know if it is really comparable. But this is fine for the purposes of that for studying the activation process over years. And the 0.22, 0.92 R square on prediction is not bad at all for this kind of application in industry. Okay, so one thing we can also do with these soft sensors is then look to the variables and see which are the most important or not, and try to also pull some information from that. We'll not cover this here, but clear here is the pressure and the reactor variables are the more important ones, and that is not a surprise, but then we have to know which reactor variables are playing a role, and that might be something interesting. So this is one type of sensors. So these are the sensors based on, data, process data. So let's now address the PAT soft sensors, so the Process Analytical Technology soft sensors. And here, what you want to do is you pick a sample from the stream whose properties you want to estimate, and you go and you measure what you want in the labs. So this is the complex, time-consuming, etc. measurement. But in this approach, you are going to explore the connection between the chemistry in the stream and that chemistry and your property. If you also can connect and relate that chemistry with some measurement from a device, then you can correlate that measurement with the property immediately. So, and here we are going to use spectroscopic measurements. Spectroscopic measurements are basically measurements that are very sensitive to detect changes in the light absorption in certain frequency bands. So that has to do with the chemistry. So if you can find a measurement, NIR, FTIR, NMR, something that correlates with the chemistry of your stream, and that the particular chemistry of your stream that is also correlated with your property, then you can, build an inferential model and use this easy, fast, and inexpensive measurement to predict your property. That's basically what you want to do here. You don't want to use all the other variables, but just a very sample that you take there and you inject into one of these technologies, the one that fit better your purposes, and then you predict it with use it to predict your response. So here your inputs are something like this. So basically they are functionals. So now, yes, now we are in the realm of function analysis, but that is something that is only recently being more brought to this field. And usually we use latent variable methods to address this. And what I want to bring here is that what is very, very important here is the preprocessing that we do with your spectra. So you have to do a lot of preprocessing, to remove noise, but also to remove undesirable effects. For instance, these different levels are meaningless. They should be the same. They just happen because there are effects like light scattering that are making this happening. So if you apply in this case, for instance, the first derivative, this will always be gone. So you should do this type of data processing here, for instance. And we also should do preprocessing to bring out the features that you really want for prediction your response. So we have to test different preprocessing, and we also have to select the most meaningful bands, because if you just have bands that are not related to the response, they will hurt your model. So you have to do band selection. And you might try different modeling procedures also. So there is all sorts of different problems that you have to address in this case in order to develop a better model. So I don't have time to go into too much detail, but here we also developed a framework that allows us to speed up this process. You can have different types of models, and for instance, partial least squares, which is a sort of golden standard for developing this type of PAT-based soft sensors. But you can also use some other PLS-based approach, like the forward interval and backward interval partial least squares, that allow you also to to select the weight band simultaneously with the model building, which is nice. And we have developed another method, which is we call multi-resolutions of sensors, that allow you to select the bands and also to optimize the resolution within each band. And our framework tests all these methods with different sorts of preprocessing. And this is basically the multi-resolutions of sensors. So it tests all these methods with different types of preprocessing. And again, we're using double cross-validation. What we also do here is we test all of them in an independent test set. And we also do replications in the test set, because you want to know how they behave, not in a single test set, but in a test set with some variability. So and in the end, we compare them all and get a plot like this. So they basically tell the different types of combinations of the models, of the preprocessing, of the bands, which one is performing better. And for instance, in this case, the model that performs better, it was with the mean centering preprocessing, and it was our multi-resolution sensor model. And we can also visualize the comparison in plots like this, where you use in the X plot, you use different sorts of preprocessing, and each line represents a different type of model. So here, in terms of the score, the best model was, again, the one that is there. But you can also see whether some model is overall the best or not. And it has been turned out that these multi-resolutions of sensors is performing quite well when we compare with all the others over the same data sets. For instance, this is a different type of application for biofuels, where you can see that method is also performing overall quite well in comparison. But let me just go back here, and so that you can see one interesting thing about this model. So now we are also predicting the raw number. It's not the same process, it came from another process. But look here, now the root mean square is 0.05. If you recall, with the process data, it was 0.4. And now it will be 0.04. So now we can be 10 times more accurate with this sort of technology than with just the process data. Of course, we have to pay for it. We have to build the infrastructure. We have to put the model there, the instrument there, and the model and the maintenance. But you can get, more accurate estimates if you can use this type of technologies. And so this also worked for the biofuels, and our method here performed also quite interestingly. This was the best one in this case for the free fatty acids. One thing you would like also to see is, in the end, go back and make the plots and see which bands are being picked for the model. That also may tell you something about the chemistry and what is being important for the property that you want to optimize. And that is also some interesting insights that you can get from here. Okay, so we have also used this sort of technology to go back and see if we can reduce the effort in the labs for making those complex measurements, because for some of the properties we can achieve error rates that meet the standards. So that means that we can now lead the company to also save some money on this without hurting any sort of accuracy in the predictions, and they can save money and have better and have more frequent measurements actually, which is also interesting for the company. So finally, what if you have both types of methods available? So in this case study, we do have a non-line analyzer, sort of analyzer as we have here. I just described a PET analyzer. I have a lab analyzer, which is a gas chromatography analyzer, 12 hours, every 12 hours. And we also have a model, sensor, that is based on process data. So how can we combine all these different approaches? So a usual candidate is, let's go for a multi-block approach. Multi-block approach is something that we can do. We compartment the different, sort of measurements in different blocks, and we handle them simultaneously, providing more or less weight to each block, and we can build a regression model like that, multi-block. But here they have different sampling rates, and that makes everything more complicated. So the way we addressed this here was with the data fusion sort of technologies. So one approach would be to use the tracked Bayesian fusion scheme, which is quite simple. You just put your model from the process variables in the common filter, and your online analyzer or your offline or lab analyzer in parallel as the measurements. And you can do some Bayesian fusion when you have both, or just use it when you have a single one, and then use them in the update. And then you apply the common filter as usual. We have also tried out other different approaches of combining these measurements. So you have tried out using in parallel 2 common filters, a bank of common filters. And what you fuse is the estimates of both common filters, which go back again, and they enter the common filter in the next stage. So there we have been learning that there are different ways of fusing, and the best way of doing data fusion is always case dependent and depends on what you want to combine, the uncertainty that you want to combine, and also the frequency with the data from each source is available. So in this case, the method that we propose was this one that also allowed to take into account some bias in one of the sensors, which is the online analyzer, which is not that accurate in this case. And if you correct for some bias, you can make it a lot better. So the kind of results that you get with this approach is something like this. So in black, you see your property that you want to estimate, which is the lab analyzer. But you also see the fused estimates, which is tracking quite well what you want to estimate. And I have not time to describe it here, but they also have inside an algorithm that allows to detect false alarms. And the tracked Bayesian fusion pretty much did well. The false alarms are in light blue. They detect most of it, with the exception of this one that was not detected. But we could detect it, this last one, with the bias correct track-to-track fusion. So this sort of fusion algorithms work quite well for fusing different sources of information. And we are working harder on pushing them forward for doing this in other scenarios where we do have heterogeneous data. Another thing that they provide is a measure of the quality of the different sources. For instance, the uncertainty here is low for the gas chromatography. Most of the times, the second better approach is the online analyzer, and the model provides usually the less reliable measurement source. But sometimes it is useful. Sometimes it is useful, and it fills some gaps where the online analyzer is not so reliable. So this is also interesting information to know where the best information came from. So just to close, I just want to bring some challenges that we are now working on. So we are working on bringing mechanistic and data-driven modeling all together. We call it hybrid modeling. Also, the multi-resolution modeling is important. We usually take for granted that the time that we have is the only one that we should work with, the time resolution. But we have been learning that if you tune your resolution, you can greatly improve your accuracy, either in time or in wavelengths. This always brings better results in our experience. Feature engineering is also very important, especially for batch processes. And actually, functional data analysis is a class of feature engineering methods. So you're going probably to hear more about feature engineering in the next future, especially on machine learning applications. Multi-block modeling is something that can also be applied instead of data fusion. It has its merits, but we should see case by case whether the best approach is to go through multi-block or data fusion. And also, machine learning, automated machine learning tools are being more applied in practice. We have applied a few of them that we just presented, but I think we should drive to other types of tools, not the automated, but the autonomous machine learning tools, which provide more flexible, uses in the future. But that is the issue for another talk. So I stop here, and I thank you very much for your attention. And of course, I will be willing to discuss any topics you find appropriate. Thank you very much.
Oh, thank you so much, Marco. That was a wonderful talk. I really enjoyed that. I like that notion of trying to integrate the first principles with the data. So very cool. I very much appreciate it. And I'm sure others did as well. Sherry, have you got any quick questions?
Yes, Ron Kennett would like to say something on digital twins. I'll unmute him. Go ahead, Ron.
The only thing I was going to ask Marco if he has some thoughts to share on digital twins. Yeah.
Thank you, Ron. Thank you so much. The digital twins, yes, is taking its course in industry. I guess in the in the manufacturing and the assembling lines, they are more advanced. Here, the models that we have available for this process that are massive are probably not at the state that we can rely them to completely, replace a factory by an accurate plant. But we are looking for them, for instance, in process monitoring. There is very interesting applications showing on there where we can somehow replace or emulate the normal operation condition variation by simulation. And for process detection and diagnosis, that is really something that can be done. That is another topic. I didn't bring here, but in the industry, what I have seen, mostly the application of twin. The twin concept was on those processes, not so much yet in the chemical process industry. I think we still have a way to go until we get enough reliable models to do it. Thank you, Ron.
Thank you, Marco. And we really appreciate that. We really need to move to the next talk. And once again, if there is time at the end, we can entertain some more questions.